On Maths with EJD, we start this new playlist on dynamical systems, which is very dear to my heart because it's my field of, should I say, expertise now. It's one area where I actually operate as a mathematical biologist, so we need a lot of concepts from dynamical systems. So get on this journey with me and have a nice time as we look at this first video, mathematical framework of dynamical systems, which is such a foundation for all the things we are set to learn in as far as this playlist is concerned. So, talking about mathematical framework of dynamical systems, our goal is to establish precise definitions and develop rigorous foundations that will help us understand different aspects of dynamical system. So we go straight to the question, what is a dynamical system? Okay, well, before we go into the technical definition, it, I mean, just get it straight that a dynamical system, as the name sounds, like even we have the English word called dynamics, right? So when something is dynamical, it means that it's changing. It's not static. It keeps changing. So we can basically say that a dynamical system is a system that evolves with time. It changes with time. Maybe it's increasing, reducing, or it's fluctuating, or whatever you want to say that to whatever you can call that, right? So the system is not static, it is changing, it is evolving over time. And many things in life is dynamic in nature, as we're going to see. So coming to the technical side of things now, a dynamical system consists of a state space X. Now, when we talk about a state space can represent some natural phenomena or anything or anything like that we can talk about. It can be maybe growth in humans, like growth in a human being, or growth in human population, and different things like that. That can be a state space. And of course, since we are talking about something that is changing, of course those changes take place over time, right? So we have a state space X, and then we have a time set T, which is a subset of real numbers or integers. Like real numbers is proper, it's particularly good for if you're looking at continuous systems, but integers are good if you're considering discrete systems where things you can have jumps like that. And then there's an evolution rule. The evolution rule can be said to be something like phi, which is t times x. You have time times space, which is mapped to the state space itself, right? So there's a state space, there's time, and then there's a rule guiding that. And the rule talks about the interaction of time and space. And then that gives us something again in the state space, such that when at time zero, at time zero, if you follow the rule, when the time is zero and you have the state, a particular point in the state space, you get that point X in that state space. So if time does not, if time is zero, right, at time zero, the state space is at that initial stage, which you can call X. But then after some time, right? So you have an evolution in the system such that phi of t plus s comma x then gives you something like phi of t comma phi of s of x. So you have something going on in the system already like this, right? So this means that evolution is consistent over time. So in a dynamical system, you have this kind of evolution going on like that. Okay, we have a very good example here. Consider dx dt equals rx. Of course, this is a differential equation of order one that can easily be solved using separation of variables. And this models population growth, and the solution is x of t equals x naught times e raised to power rt. So in this case now, this x can represent population size, and we have the flow, which is the flow of this is talking about exponential growth. In fact, this e raised by rt means that there's exponential growth. In case you're wondering how to solve differential equations, I have a playlist on differential equations, like with I think about 87 videos, and it covers ordinary differential equations, uh, partial differential equations, and so things like Laplace transforms, which help to solve differential equations. So I'm trying to navigate to that now. So I actually split it up, but if you want to see everything in one place, you just go for differential equations. So these differential equations now consist of the 27 videos on partial differential equations, 39 videos on ordinary differential equations, and of course 21 videos on Laplace. So that makes all these 87 videos on partial differential equations. So this is an aggregation of all of that, like this. So, introduction to differential equations. So you go all the way down talking about all this, and then at some point we had to talk about Laplace transform. And then later on, I went ahead to talk about partial differential equations. That's the last part of that. And of course, some numerical analysis came into it because at some point, I mean, when things get very complicated, you cannot get closed form or what you call analytical solutions. So you need numerical approaches, and that's why I also brought some videos from numerical analysis into that to make 87 videos. So once you have this playlist on differential equations, you have everything you ever need about differential equations. At least almost everything you need about differential equations, like that. So that's the basis for some of the things we'll be doing under dynamical systems. So for instance, you have dx dt equals rx, you know, um, so you can use one of the simplest methods, one of the basic methods, because the system is very simple to solve for x. So you have dx dt equals rx. So to solve this now, so you can see dx here, you can see x here. So you can use what is called the separation of variables, separation of variables. And the way to do that is you can divide through by x first of all. So you have like 1 over x dx dt equals r. Then another thing you can do is you can multiply through by dt. So you have 1 over x dx equals r dt. Okay, so by doing this, you have separated the variables. So then you can integrate, right? So to solve differential equations, you get to integrate. So you integrate 1 over x dx equals integral of r dt. So from here now, this r, of course, is some kind of constant. So here you have integral of 1 over x dx equals r is constant, so we can take it out and we have integral of dt. When you integrate 1 over x, you get ln x. That's the natural logarithm of x, and that is equal to r now. When you integrate dt, when you integrate dt, of course, you get t there. Of course, you need an arbitrary constant, which you can call, say, if you like, you can call that k. All right. But then we are looking for x. So we need to isolate x. And you can see the natural logarithm is disturbing x like that. So the way to take care of that is take the exponents of both sides. So you have e raised power ln x equals e raised power rt plus k. All right. So in this case now, e raised power ln x simply means x. So to neutralize natural logarithm, you take the exponent to and you can also go the reverse. So with this now, this can cancel this. So we have x, and this is equal to e raised power rt plus k. But then we have to, tidy this up a little bit more, because this is x equals e raised power rt times e raised power k. So this e raised power k is some kind of constant, right? So we say x is equal to, you know, if this constant is maybe some small c, and we have c e raised power rt. So this is what we call the general solution. General solution. Okay. But if you want to get the particular solution, you can still go ahead, right? So to get the particular solution, you can then say, then in that case, you need an initial condition. So given an initial condition, say you have x of 0 equals x naught, right? So what this simply means is that at t equals 0, x is equal to x naught. That's what that simply means. So in that case now, of course, this expression itself can be written as x of t equals ce raised to power rt. So in that case now, at t equals 0, x equals x naught, right? So that means here, this is now x of 0 equals cer into 0, because t is now 0, okay? But of course, this x of 0 is x naught. I mean, yeah. So this is x naught now. X raised by x of 0 into c r times 0 is 0. So here now you have x naught equals c. So since x naught is equal to c, you can then go back to the original thing that so you can then say, so x of t is equal to, since c is x naught, so we have x naught e raised power rt, and this is now the this is now the what we can call the specific or particular solution. Particular solution. So in this case now, um, what the general solution it gives it tells you the general solution is such that you can have a family of curves depending on the value of C. But given this particular initial condition, we have this specific solution to the problem. And that's what you see on this page here. All right. So this models, so if in this case now, this actually models population growth. And if you plot this graph, you see that the most important part of this is this e raised power rt, and because e raised power rt, uh, taking that r is positive, and of course, if it is positive like that, we are going to have a population explosion. So, and that's why we have exponential growth in that situation. Okay, so we move on to state space and phase space. All right, state space and phase space. So, we started the idea of dynamical system with, the need for a state space, one, then we have time, and then we have a rule that governs the evolution. Okay. So the state space is the set of all possible states. So you have a particular state, and then if you have more than one state space, then you have what you call a phase space. Now, when I was talking about the uh, on the linear algebra playlist, there was a point I got when I was talking about the applications of linear algebra in data science, and one of the key things there is that we have we have um we have variable space, right? We have a variables. We have a variable. We have a feature, yeah. We have a feature, but then when you have more than one feature, you then have a feature space. For instance, maybe you want to you are trying to talk about the BMI of people, and in that case now you need the weight, you need the height. Maybe you also need the age there. So the age, the weight, the height, each of these are features, but then when you put them all together, they become a feature space, right? In that case, you have a three-dimensional thing like that. So here we're talking about state space and phase space. So the state space is the set of all possible states, right? So an example is when you have a pendulum, you are talking in two dimensions, right? You're talking about probably angle and you're talking about space and time or something like that. For weather, I mean weather is multi-dimensional. You have r raised power 10 raised power 7. Then you also have a logistic map, which is more like the discrete thing. So here you see that the phase space is a geometric representation of the state space. So the state space is a collection of all possible states. Like the other time we talked about population growth and things like that, right? So if you have population growth and some other states, you have a state space. But if you now have to represent that geometrically, then you have a state. Uh, you have a phase space. So if you represent the state space in geometric form, you get a phase space. So each point represents one state in that space like that. So then we go ahead to talk about orbits. For an initial condition x naught, the orbit is O x naught equals phi, the rule, right, that combines time and the initial condition such that time belongs to the general time space. So basically, the orbit is the trajectory traced in phase space. So, you have a phase space. If you're talking about like a pendulum in two dimensions, for instance, so maybe you're talking about time and space and all that. So the trajectory is the motion followed or the path followed in the phase space, especially in geometrical form. So imagine this very simple example. Consider that x dot is equal to x. X dot simply means dx dt, right? So dx dt is equal to x. So just like what we did the other time, you can separate variables and you have 1 over x dx equals dt. And then if you do all that, the only thing you don't have here is there's no rx here. So it's about the same thing except that there's no r in the solution because there's no r in the problem too, in the question. So if you solve this, if you follow the same thing I did, you get x of t equals x naught e raised power t. So the orbit is an exponential curve. So exponential because you have e raised power t. If you had e raised power minus t, it would have been like a decay curve because e raised power t means things are blowing up, whereas decay, well, I mean, how do you even visualize that? You can see the key components of that using a tool like, say, Desmos. Okay, So to see e raised power x, e raised power t, we can just say e raised power x, right? E raised power x, you see, you have that blowing up. It just keeps going forever and ever. But on the other hand, if you have e raised to power minus x, so you have a system that is dying out. It's decaying. So you see, this one is coming from somewhere, and then it just dying out like that. So you have all these things. So these are things we are going to come across as we speak about dynamical systems. Now, let's talk about continuous versus discrete time systems, right? So, um, of course, basically, even we come across this idea of continuous and discrete, right? For continuous, right, you cannot split it up. Of course, you can discretize a continuous system, but the idea of continuous is that you just have maybe you have something moving from 0 to 1 without you can't pinpoint you can't split it up like that. But for discrete systems, you are talking about a countable system. So a continuous system, it's like smooth flow like that. But discrete, like like you have jumps, you're taking steps like that. So for a continuous time system, it is defined generally by dx dt equals f of x. So when you see the differential equation like this, you're basically talking about a continuous time system. A very good example is what we saw. Okay, like this one is x dot equals minus x. So in this case now, if you solve this, you're most likely going to get x dot. Here we saw x dot equals x. So you got x naught e raised power t. Here you're going to get x naught e raised power minus t. So it is going to give this other result, e raised power minus x like this. So whatever you multiply by it, it's just a matter of what the value is going to shift. For instance, if say the x naught is 3, so you just have this shift up here like this. Then if this one is also 3, you just have it coming up to meet at 3 like that too. But if not, it just goes start from 1 like this. Okay, so that's just the change that happens in that case. Okay, so that's for continuous time. So let's talk about discrete time. In discrete time, you have something like this. It is defined by xn plus 1 equals f of xn. That means that x1 is equal to f of x naught. So you evaluate the function at x naught, then you get x1. So to get x2, you evaluate the function at x1, and that keeps going like that. That's the idea of discrete. So you're moving step by step like that. So a very good example of a discrete system would be this xn plus 1 equals rxn into 1 minus xn, which is popularly called a logistic map. Okay. Thankfully, I have Python codes to demonstrate some of these ideas in this whole playlist. So far we've talked about continuous and discrete. So when you talk about for continuous time, right? The time for continuous system, the time is in the real number system. So it can be whole number, it can be fraction, it can be rational, it can be irrational. All of those are accommodated here. But for discrete, you're talking about integer times. So you're talking about count, step one, step two, and all that. The tool you use for continuous systems is the ordinary differential equations. Then for discrete system, you use iterations, like just like I demonstrated the other time. To get x1, you evaluate the function at x naught. To get x2, you evaluate the function at x2, and so on. And then you have another feature here. So map. For the continuous system, the map is a flow, like it just keeps going, like it just flows continuously. And for discrete, the map is an iteration, like you have to count step by step. Now let's look at this Python code that takes care of this. Imagine we have, so in this case now, imagine you have rx into 1 minus x. That's what we are trying to demonstrate here. So if the r is, which is usually taken to be like growth rate, is 3.5, and the state space is 0.2, maybe some initial condition, and n is 100. So we want to do 100 steps, because this is about iterations, because uh this is discrete, right? So you just say so you initialize, you have values, you open this list, and then for everything in the range n is 100. So it means you're starting from 0 to 100, and then you evaluate x. So r times x into 1 minus x. Okay, so you have x into, so this is more like some kind of initial condition. So you have x into r into x into 1 minus x, and then you have values append x. So you start with that x and you keep incrementing until you finish all the 100 iterations. All right. So if you run this now, We just get this. Can you imagine this beautiful plot? We get that starting from 100 to, I mean, starting from 0 to 100. So n here talks about the number of iterations. So you can see, you can count this. So this is first iteration, second, third, and so on until you get to the hundreds. And you have all your xn here. So the xn values are on this other side because that's what we're plotting at last. So you're plotting n against xn. So step one, you have the xn value. So like when n is 1, right, you get x2. When n is 0, you get x1, and so on and so forth. And that's exactly what we have like this. So then we come back to talk about flows. So the flow talks about the movement of the state space. How is it moving? Is it moving freely, or it is moving step by step? So a flow is a family phi t, with t being real, such that phi naught is id. That's like the identity of the initial condition, the initial state. And then you have phi t of s is now phi t. So this is now interaction between time and space right here, and it is generated by x dot equals f of x. So then you then have that phi t of x naught is equal to x of t. So of course the state space you have is determined by the initial condition. So at the initial level you have an assigned value, but then along the line, as time passes, you then have the interaction between time and space like that. So then you have semi-flows and time t maps. Okay, semi-flows and time t maps. A semi-flow is defined for t greater than or equal to 0. Okay, so for t greater than or equal to 0, in this case, a time t map is ft of x equals 0 sub t of x. Now, when you talk about time t maps, right, they are basically, time cannot be negative, all right, and that's why the flow is semi, because you only talk about the positive side of things from time t equals 0 or greater than 0. So what about the negative side? No, because time, there's nothing like negative time, right? So that's a time t map. So it converts continuous dynamics into discrete dynamics in this case. So a time t map converts a continuous dynamics into discrete dynamics. A very good example of that would be this. You have x dot equals minus x. So the solution, of course, like I said before, is x of t equals x naught e raised power minus t. So the time one map in this case, if you use this formula that f sub t x equals phi t of x, you're simply just going to get f that's f sub t of x. So the t here is 1. It's if you have a time one map, it is time t map. So t here is 1. So f1 of x equals phi t of x. So phi t of x here now is phi t of x. So since this is what we have, this is phi t of x. So we substitute x for t there. So we have e so x naught now is now x, then t is 1 because that's time one map. Then we can then represent that here. So we have of course, in case you're new to Python, right? If you want to check out my playlist on Python, I actually did a thorough job of moving through the whole of Python from the very basic level. I think this is it. Yeah, Python basics with EJD. So there I started from very simple concepts from introduction to Python all the way down to you know Python packages and everything. So if you have never learned Python before, you can take this up step by step and become a master of Python if you can follow. Because interestingly, if you look at the description box, I have links to materials, to the code sheets which you can download so you can follow step by step. Okay, so here now we have, if you take the initial condition to be 2, right? And our time six, we are moving from 0 to 5 in 200 divisions. And then we're working with x, the solution, x naught e raised power minus t. That's the solution to x dot equals minus x. So that's what we are plotting here. So I just run that and we get the plot. So it's just if this the flow of the x dt equals minus x. So like I said, x dot is equal to x. I mean, x dot is the same thing as dx dt. Okay. Another way to do that can be say f prime of t. So another notation you may have sometimes is x prime, which is the same thing as dx, which is still the in this case, right? This can be said to be like the so when some people take this to mean change with respect to time, and some people take this to mean like change with respect to space. But I mean, it's not there's no hard and fast rule about it. Just do whatever works for you, or just follow the definition you have in whatever system you're using. Um, so follow that. So you see the flow here. And then next thing we move on to determinism. Okay. Determinism is like, oh, it's like a, a, I think the best way to say it is that there's a rule you must follow, okay? The rule cannot be bent. That's the idea of determinism. So, and that's why when you say a system is deterministic, there's no randomness in it. It is always unique. So a system is deterministic if the initial x of 0 is equal to x naught. So if the initial condition implies that x of t is unique. So if the initial condition determines what happens afterwards, then that's a deterministic equation. The opposite of determinism is stochasticism. That's if you don't if a system is either deterministic or stochastic. So in the stochastic system, the initial condition has nothing to do with the trajectory of the system, right? In that case, yeah, it is stochastic. It is there's a lot of probability. You can talk about noise and uncertainty. But for determinism, a deterministic system is certain. There's no randomness. You can so whatever you get next is determined by what you got before. And then it's closely associated with the idea of determinism is reversibility. So a system is reversible if phi sub minus t is the same thing as phi t raised by minus 1. So in that case, now backward time exists. That is saying that what is happening now, you can use it to determine what happened in the back, right? What happened previously? Like one idea that comes to my head right now is maybe if someone goes for a psychology session for psychotherapy, right? So the therapist would ask you about how you grew up, the kind of environment and things like that, and that can then help them to have an idea uh like whatever. So that's owing to the fact that whatever you might be now is as a result of where you're coming from. So that's a non-mathematical way to explain this the dynamical system concept of reversibility, and this simply talks about the fact that backward time does exist. So a very good example, you have x dot equals x, which we've been seeing all along. So x dot equals x is reversible, whereas this is x dot equals square root of x is not reversible, right? So this is a reversible system, whereas this is not reversible. So, and we talk about well-posedness. So well-posedness is something that really comes up every time when we talk about when we talk about dynamical systems, right? So for well-posedness, so the fact that there's a problem does not mean that a problem is a good problem. There are bad problems, right? So a problem is well posed. For instance, how do you know a problem is good? That's the idea of well-posedness. Now, a problem is well posed if solutions exist, and apart from the fact that the solutions exist, the solutions are also unique. So if you solve it several times, you don't get different solutions. And that's not true of stochastic systems. So you can solve 100 times and get 100 different results in the stochastic system. But if you solve a deterministic system, if you solve it 1 million times, you get the same result each time because it is in that case, you say the problem is well posed. Maybe I'm modeling things up right here, but when we talk about well posedness, a problem is well posed if solutions exist, solutions are unique, and so the solutions depend continuously on data. That gives a hint to the determinism of a well posed problem. So small changes in initial data produce small changes in solutions. That's what it means. So you can be sure. But in a stochastic situation, a small change can cause a large problem, right? And we see things like that when you talk about weather, for instance, right? That talks about some things like the butterfly effect and all that. So that the idea of butterfly effect is that a butterfly flapping its wing in one corner of the earth can lead to hurricane in another corner of the earth. That's the idea of a stochastic system, and it can lead to chaos easily. So Then we talk about existence and uniqueness. If you consider x dot equals f of x and the initial condition x of 0 equals x naught. Now, if f is Lipschitz continuous, now we are coming across the idea of Lipschitz continuous for the first time, right? So I want to talk about that. So if f is Lipschitz continuous, then we say that a unique local solution exists. Now, so you have the system that x dot equals f of x, which represents a continuous system and it has an initial condition. So if it is Lipschitz continuous, then we say that a unique local solution exists. Now the question is, what is Lipschitz condition, right? So the Lipschitz condition is straightforward. It is this that you say that a function f is Lipschitz if the absolute value of f of x minus f of y is always less than or equal to L multiplied by x, the absolute value of x minus y for some constant Ly, right? So in this case now, so you have 2 points x and y. So if the difference between the two functions is always, the absolute value of the difference is always less than or equal to a constant multiplied by the difference between the input values, the independent variables, right? So for some constant L, then you say f, the function, whatever function, that's this function f of x, then you say it is Lipschitz continuous. A very good example of this would be that x dot equals x squared. So here you see that f of x is x squared. So you see it is locally Lipschitz because if you fix it in here, so f of x minus f of y, that is like x squared minus y squared will be less than or equal to. Aha, I think I can really demonstrate this. So the simple thing about Lipschitz is this fact that you say if a function is Lipschitz continuous, so a function, okay, is Lipschitz. Hope I got that right. That spelling can be quite a lot. Lipschitz, SH, okay, SCH, Lip Lipschitz, Lipschitz, continuous, okay, continuous. If the absolute value of f of x minus f of y is always less than or equal to a constant L multiplied by x minus y. So, and we said a good example would be this function that, I mean, for this equation, x dot equals x squared. So here now, we know that the general term is x equals f of x. So here f of x is equal to x squared. So if that is the case, it means that f of y is also equal to y squared. So if we want to go for the Lipschitz thing now, we just know this is absolute value of absolute value of x squared, all right, minus y squared, which is, of course, this is less than or equal to the absolute value of x minus y into x plus y, if you like. Okay. And then in this case now, we can have x squared minus y squared. X squared minus y squared is less than or equal to absolute value of x plus y into absolute value of x minus y. So if you take this as some constant L, then we have that absolute value of x squared minus y squared is less than or equal to L multiplied by x minus y. So in this case now, see the function is actually Lipschitz continuous like that. So that's the Lipschitz. So it satisfies the Lipschitz condition. So f of x equals x squared is locally Lipschitz. Therefore, solutions. So because of this Lipschitz situation, that we can say that this problem has a unique solution, right? So example 2, in this case, which is we have a non-unique situation, x dot equals, this is serious, x dot equals the square root of absolute value of x. So of course, this is not Lipschitz at x equals 0. So at x equals 0, x dot is 0. So there's nothing to talk about there. So, and you have one of the possible solutions if you solve this is x of t equals 0, or x of t is t minus c all over t minus c squared over 4. So these are some possible solutions to that problem. Okay. So if you look at then if you now look at the problem itself, right? You want to solve that ODE, x dot equals x squared. Okay, so then we are bringing the sub IVP initial value problem solution. So if you want to look at numerical solution to problems, you can check the differential equations playlist where I talked about all of this a lot. So we are solving this now as an initial value problem like this. So okay, we'll just go for this now. And this is what we get. We have this serious situation of blowing up. It moves so fast like this. Okay, so in this case now, there's no unique solution. That's what this situation. No, this is not the case. This is the case of solution, yes. So this is the case of possibility of solution. So we move on to the next thing. We talk about maximal interval of existence. So um the idea of maximal interval of existence simply tells us that for a solution that a solution exists within an interval with a minimum value of t and a maximum value of t. So it means that the solution cannot be extended beyond this minimum and maximum interval. So that's what you call the maximal interval of existence. A very good example, like what we just saw, x dot is x squared with initial condition x of 0 equals 1. Okay, so the solution to this is xt equals 1 over minus t. We can still use, I think we can still use separation of variables here. So solution is xt equals 1 over minus t. And so if you look at this now, this blows up at t equals minus 1, t equals 1. So because here now, 1 minus, at t equals 1, 1 minus 1 is 0. So 1 over 0 is undefined. So it blows up at t equals 1. So in this case now, the maximum interval of existence, the maximum value of t will have to be 1. So it can come from anywhere, but then you can't get, can it come from anywhere really? Yeah, maybe from 0 to 1 now. So from 0 to 1. So because beyond t, you can't get, in fact, at t upwards, you can't get any sensible results. And that's exactly what this place tells us. You see, x equals 1 over 1 minus t, which is the solution to that problem. So we have that right here. So you see that at 1, everything just, it's behaving well until as it gets closer and closer to 1, it starts blowing up. So we have a finite time blow up in that situation because the solution has a maximal interval of existence where one is at the is that one is the at the top. That is one must not be reached. That's what that implies. Then we have forward and backward time. Okay, so for forward time, t is greater than or equal to 0. This is used in most applied models. So for backward time, now t is less than or equal to 0, which doesn't make sense particularly, but for the sake of reversibility, we have that. So it requires reversibility when we talk about backward time. Okay, for forward and backward time now. So we have examples like this. Forward only, you have x dot equals root x with initial condition x of 0 equals 0. So for this is for forward only, but for backward only, we have x dot equals minus x. And the physical meaning of this, so Newtonian, yes. For a Newtonian system, backward is possible. For a diffusion system, backward is not possible. For a population system, backward is not possible, right? So we have that. Then we have a unified view of everything we've been talking about all along. So we see here that we can have a continuous function which is represented as x dot equals f of x, and that implies phi of t. And then we have a discrete system where we have x of n plus 1 equals f of xn, which implies f power n. And both satisfy the idea that in time and space, you have phi of t interacting with phi of s, where time is where t is time and s is space. Okay. So that gives you the evolution of the system. Then we have a concept map from everything we've been saying so far. You have the state space with its flow, its orbits, and stability, and that leads to existence, uniqueness, and well-posedness. And then that leads us to the idea of maximal interval and time direction as to whether you have forward or backward time. In summary, we have talked about these things so far. We have state space, the meaning of state space, State space talks about all possible states you have in a dynamical system. You have orbit that talks about trajectory, the path taken by this by a particular by the system. Then you have the flow, which is about continuous evolution. You have semi-flow or semi-flow, I don't know. That's forward only. Then you have determinism. Determinism that talks about a unique feature, right? Like there's no randomness in the system. Whatever you have at this point determines what happens next. Then you have reversibility. So reversibility has to relate with backward time. Then a system is well posed if there are stable solutions, like we said. Then you have there's Lindenhoff that talks about existence theorem. I think we're going to come across it sometime in the future. And we talk about if a system is a problem is well posed, right? It has a unique solution. The solution exists and it is unique like that. I think there's one more condition. Yeah, and it is always backed. It's evolves based on data, and then you have maximal interval, which talks about the domain of existence of the state of yeah, of whatever you're dealing with. So we have some practice problems here. Solve all problems carefully, show full reasoning and computations. Let x be r, that's real number, and define this to be x raised to t. Verify that phi satisfies, those conditions for what a dynamical system is. Now you can then conclude if phi defines a dynamical system. Of course, from what I see here, x e raised to t defines a dynamical system if you follow all that. So at time t, for instance, at time t equals 0, so you're just going to have x. That is correct. Then at time t equals t plus s, you can have x, you can have your t, you can isolate t and then have s and x interacting like that. Then for problem 2 now, consider the system x dot equals minus 2x. Find the explicit solution x of t. Of course, the explicit solution is just going to follow the idea of x, like what I did the other time. So most likely the solution here is going to be x naught e raised power minus 2t, you know, x naught e raised power minus 2t. Then you describe the orbit through x naught. So you're going to have based on whatever the x naught is, you're going to have a decay kind of growth. And instead of exponential like we saw before, it's going to be decay because of the negative sign. Then you can sketch the orbit in phase space. All right. Then discrete time system, you have xn plus 1 equals this. Compute x1, x2, x3. Of course, this one, to compute x1, that means n equals 0. So you have x1 equals 3x naught, 1 minus x naught. So in that case now, x1 is 3 times 0.2 into 1 minus 0.2. That's 3 times 0.2 times 0.8. You multiply that, you get x1. So with x1, you then go back for x2. So x2 now will be 3x1, 1 minus x1. So that x1, you got to put it back there. So, and you keep doing that until you get x3. Determine whether the sequence converges or oscillates. Okay, the answers you get to tell you that. Then you can use the computer to visualize the first 50 iterates. So you can use Python to get that as many times as possible. Then you can have flow property. Let phi sub t of x be x plus t. Verify that phi sub t satisfies the flow properties. Then find the differential equation that generates this flow. Then interpret the physical meaning like that. You want to try that out. Then for semi-flow, we have x dot equals root x. So which is x into 0, with initial condition x of 0 equals 1. So you want to solve the differential equation. I think separation of variables can still work here. Then determine the maximal interval of existence. You're possibly going to have a situation where at a particular value, the system will not exist. Then you want to explain why this defines only a semi-flow. Then we have determinism and reversibility. X dot is minus x cubed. Show that the system is deterministic. Determine whether it is reversible. Justify your answer mathematically. So you can look at the things we talked about before. Then for Lipschitz condition, f of x is absolute value of x raised to power half. Show that f is not Lipschitz at x equals 0. Okay, one at x equals 0, you don't have that there. So explain how this affects uniqueness and give an example of two distinct solutions with the same initial data. So in that case, there's no unique solution. So you can get you're going to get a couple of solutions instead of a unique one. So you have the Picard-Lindenlov application. X dot is 1 plus x squared. X of 0 is 0. Verify that f of x is 1 plus x squared is Lipschitz on bounded intervals. So you can do the kind of thing I did the other time. Then you apply the Picadilly, I love to prove local existence. Then find the explicit solution. Then we have finite time blow up. So x dot is x cubed, x of 0 is 1. Solve the differential equation, find the maximal interval of existence, and determine the blow up time. Okay, then we have the forward and backward time thing. So here, um, consider x dot equals x into 1 minus x. Find all equilibrium points. Analyze the behavior as t approaches infinity. Determine whether solutions can be extended backward for all time. Interpret the results physically. So, since we've not talked about equilibrium point here, this may be a bit difficult, but in the next video, I'll be talking about ideas around equilibrium point. As we move on, I'll be talking about uh, you know, theory ways of dealing with ordinary differential equations without having to solve them explicitly. Okay, thank you so much for listening to this beautiful first video on dynamical systems. I know it's been a nice one and there's so much more coming, so you want to brace up and enjoy, have a nice time looking through this whole thing. Let me know how helpful this is for you, and if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. And if you have not, you don't want to keep missing out on this channel, go ahead and subscribe right away. Hit the notification bell so you can always get alerted each time a new video is released. And beyond that, you can also become a member of this channel by clicking on join. So once you get to my page, you see join and you see levels of membership that gives you some special privileges, as you'll see there. Okay. Ultimately, don't forget to comment, like, and share so that more people can have access to the great things I have going on here. Till I come your way again, keep doing maths right. Bye.